Ina Crespo rode 7.5 miles down the Habashabi River in 1.5 hours, but the return trip took her 2.5 hours. Find the rate Ina rose in still water and the rate of the current. So the first thing that we want to do is to assign variables to the unknown quantities. So this problem has two unknowns. We first of all want to find the rate Ina rose in still water. Let's use x to represent that quantity. So x will represent the rate Ina rose in still water. We also need to find the rate of the current, so we'll pick a different variable to represent that amount. Let's use the letter y. So x is the rate that Ina rose in still water, and y is the rate of the current. The next thing that we'll do is we'll organize the information in a table. And I guess prior to that, notice that as we read through this problem, it talks about distance, it talks about rate, it talks about time. So in the back of our mind, we want to recall that distance is equal to rate times time. Distance is equal to rate times time. So as we fill in or organize our information, we'll make one column that contains distance, another column that contains rate, and another column that contains time. Now Ina rode downstream, so we'll have downstream and then on her return trip she was rowing upstream. Ina Crespo rode 7.5 miles downstream, so we can fill in 7.5 for the distance downstream. It says that it took her 1.5 hours. The return trip we'll assume was the same distance, 7.5 miles. But because she was going against the current, it took her longer. It took her 2.5 hours. Now the thing that's a little bit tricky is determining, well, what was the rate? What was the rate going downstream and what was the rate going upstream? Well, Ina's rate in still water is x. So we'll put an x in each. But as she's going downstream, the water is not still. The water has a current, and that current is helping Ina to go faster. So what we want to do is to add the speed of the current to her speed in still water. On the other hand, when she's rowing upstream, the current is going to slow her down. And so we'll take away y from x, her normal speed minus the speed of the current. So in order to get our equations, we use the fact that distance is equal to rate times time. So for our first equation, we'll have 7.5 is equal to rate x plus y multiplied by 1.5. And for the second equation, 7.5 is equal to x minus y times 2.5. What we need to do now is to solve this system of equations. Now what I notice is that y and minus y, those are opposites, so it would be real nice if we could add these equations together, but unfortunately we have a 1.5 that's being multiplied by one and 2.5 that's being multiplied by the other. So let's go ahead and divide both sides of the first equation by 1.5 and divide both sides of the second equation by 2.5. So for the first equation, we're dividing both sides by 1.5. 7.5 divided by 1.5 is equal to 5. So the first equation becomes 5 is equal to x plus y. For the second equation, we'll divide both sides by 2.5. 7.5 divided by 2.5 is equal to 3. So the second equation becomes 3 is equal to x minus y. So we had our original two equations, and then now we have our two new equations. In the two new equations, the coefficients of y are opposites of one another, so we can go ahead and use the elimination method and add the two equations together. When we add the two equations together, we get 5 plus 3, which is 8, x plus x, which is 2x, and y minus y is 0. So we have just 8 is equal to 2x, divide both sides by 2, and we discover that x is equal to 4. X is equal to 4. So what does x represent? X represents the rate Ina rows in still water. So Ina could row 4 miles per hour in still water. We still need to figure out the rate of the current. So in order to find the rate of the current, we can use one of our two equations, or use any of these equations, substitute 4 for x, and then solve for y. So let's say we use this equation right here. 5 is equal to x plus y. Then we would have 5 is equal to x, which is 4, plus y. Subtracting 4 from both sides gives us y is equal to 1. So y is equal to 1. Y represents the rate of the current. The current flows 1 mile per hour.